Greetings and welcome, friends. Mr. Waddy here. We're in section 5.3. We're solving systems of equations, linear equations, the thing that we've been doing all chapter so far. And we're learning a third technique. So far, we know how to solve by graphing, finding the intersection of the two lines. We know how to solve by substitution, where I solve one of the equations for one of its variables, plug it into the other equation for that variable, solve for the first solution, and then plug that solution into the revised equation to find the second. All right, so we've done those two, and now we're going to use linear equations, solving them by elimination method. All right, elimination method is going to be perfect for those situations when you don't have a weak spot, quote unquote, right? When one of our variables doesn't have a positive one or negative one coefficient. Elimination method will be the means you want to solve to bust through all of that extra armor of those leading coefficients. But one of the things that happens during this that I want to justify, it says add the equations together to eliminate one of the variables. And I'm not going to give you a formal proof as to why this works, but I just kind of want to show why this could work. All right. So here I've got my Desmos graphing set up. I've got a system of equations, and they have a solution at 4, 1. Notice, first of all, what if I was to multiply this equation through by 2? Now, I can do that using the multiplication property of equality, and we know from back in our early days of algebra that multiplying both sides of an equation by 2 is a legitimate means of doing things. Let me show you what happens graphically to the blue line if I double it. All right, so 2x plus, and instead of 4y, what if I have 8y? And what if instead of equals 8, I have equals 16? Wait a minute, what just happened? Where's the green line and the blue line with respect to each other? They're the same line. They're exactly the same. My green line and my blue line are actually right on top of each other. And so the intersection that the red line has with this green line is going to be the same. All right, so I can double an equation. I could even multiply it by a -2. What if I make that negative and this negative and, here we go, this negative, -16. It's still the same equation. What? It's the same line. You can multiply it, you could divide it, you could do all of those things, and using those properties of equality, you'd end up with the same thing. Now here, what if I ask this question? What if I was to add these two equations together? All right, and that's a really weird idea, and that is the idea that this is suggesting here. Add or subtract the equations together. What? That is so weird, and I just want to show you what happens and why it's helpful to us. If I add 2x and x together, how many x's would I have? 3 x's. All right. If I add -3y and plus 4y, a little bit trickier, how many y's do I have? Or 4y minus 3y is positive y. And if I add 5 and 8 together, what do I get? 13. So I get a green line, which is neither the blue or the red line. But notice, what special quality does it have? Why would this green line be helpful to us? What does it share with the red and the blue line? Not the slope, it's steeper, but it shares the same intersection. These lines all have the same intersection. So I could add these two equations together. I get a completely new equation, but it has the same intersection. So in terms of a system, if I add two equations together, or even if I subtract them, let's actually do a subtraction one. Let's see, can I actually drag this down? Will it let me do that? Oh, look at that. Wow, didn't even know that was a feature. Good job, Desmos. Let's subtract them. Let's do 2x minus x, and I would get 1x. If I do -3y minus 4y, I would get -7y. And if I do 5 minus 8, I would get -3. Notice this new purple line. I subtracted those equations, and what special quality does this purple line have? They intersect at the same point. And when it comes to solving systems, I really only care about their intersection. I don't care about where their slope is, what their slope is, or what their y-intercept is. All I care about is their intersection. So if it's helpful to me to add or subtract equations together, and if it somehow makes my problem simpler, I want to point out that I get exactly the same intersection, which is the only thing that I need to maintain or to be consistent. All right, so this is not a formal proof as to why you can add equations together in elimination method, and it's still helpful to us. But I hope that you kind of at least see, like, okay, it's keeping the same intersection even though I have a completely new line. All right, so that's the only thing I wanted you to take away from that, as to justify why that step works. So elimination method is going to have more steps, okay? More steps, but it is more powerful than substitution. And all of the problems we do today are going to have step one done. All right, so I'm handing you problems where, like, just like with T-ball, right? Don't worry about it being a curveball or underhand, whatever, nothing. It's just gonna stay here on this post, and we're just gonna be knocking these out of the park all day today. Actually, you probably weren't hitting, grand slams when you were in T-ball. If you were, you're probably not in my class right now. You're probably like a professional baseball player. But anyways, we're going to have problems that have step one done, and we're going to specifically aim on, okay, what about these steps? How could I bring this to completion? Tomorrow we'll worry about problems in which step one is not done, and it'll be interesting. We'll see. So let's do this problem. All right. So here's a how you solve by elimination method. Okay, and you'll see why it's called elimination method in a moment. So here's example one. You already have this written down. It says solve the system of linear equations by elimination. Now, we could solve this by graphing. We could solve this by substitution, but notice there is no weak spot here. And if I tried solving this by substitution, which we could successfully, I would have to trudge through the mire, the long dark of Moria, right? Go through the swamp of sorrows of lots of fractions to get to that solution, which we could, all right? But elimination method is going to be the stronger method when dealing with a system that has no weak spot. And so I want to point out, first of all, step one is done. All right, what do I mean by that? What was step one? We'll at least read it. Okay, it says multiply, if necessary, so for us it's not, one or both equations by some number so that at least one pair of like terms, all right, the variables, has the same or opposite coefficients. All right, I'm going to usually have us aim for opposite coefficients. So why is step one done here? Well, step one is done because, notice in this problem, the two y's have opposite coefficients. Actually, I'll even highlight them just like we would lock on before. The y's have opposite coefficients. Coefficients are the number in front of a variable, right, that are being multiplied by that variable. In this first equation, it's 2y. In the second equation, it's negative 2y. So the coefficient is the positive 2 and the negative 2. So these are opposite coefficients, and so step one is done for me. All right, my goal is have two of my variables to have opposite coefficients, and that's done. All right, so step one done. Step two, add or subtract. We're going to specifically, so when we do this, we're pretty much going to avoid the opposite and we're going to avoid the subtract. Even on your notes, you guys can cross those out. We're gonna add. My bad. We're gonna avoid the same coefficients. We're only gonna do opposite, and we're gonna add them. My apologies. Oh man, you guys probably just crossed that out, and now you're like trying to erase it. Oh, so sad. So sad. I'm sorry. So, all right, we're gonna add these equations together to eliminate one of the variables. Oh, that was the word of the day, elimination. So let's see how this works. So if I add these equations together, all right, you could literally watch this. I'm going to put like an addition bar underneath it almost is what I'm doing, right? I don't have to put that plus sign there necessarily, but I'm adding them vertically together, all right? So 3x plus 3x are how many x's? 6x. 2y plus negative 2y is how many y's? 0y. Oi, right? Which is no y's. Notice that it got eliminated. All right, that's wonderful for us. That's what we wanted. We wanted those to be eliminated, hence the name elimination method, okay? And the reason they were eliminated, notice, was because they had opposite coefficients that they were able to like cancel each other out perfectly. And oddly enough, yeah, these ended up getting eliminated too. That wasn't something that we had to have happen. So 4 and -4 had to be 0. So let's see. So what did I added them together and they were eliminated. What do they do? Okay, so step 3, solve the resulting equation. So I get a brand new equation, and this equation would have been a line that has the same intersection as the other two. I don't even know what that intersection is yet, but that's fine. How do I solve this equation for x? It's being multiplied by 6, so I'll do the inverse, which is division, and I'll get x equals 0 divided by 6 is 0. Yeah, not bad. All right, and okay, so I've got half of my answer here. And for step 4, what did it tell me to do? All right, let's see. Step 4, substitute the value from step 3 into one of the original, either of the original equations and solve for the other variable. Okay, we can do that. So I'm going to take this. Which equation looks easier to work with? Maybe the first one. It's got all positives. I don't know. So I'm going to plug this in for this equation's x. So I'll have 3 times 0 plus 2y equals 4. And 3 times 0 is 0, so that's just 2y equals 4. And how do I solve for y? Y is being multiplied by 2. What's the inverse? Divide both sides by 2. So I'll have y equals 4 divided by 2 is 2. So my solution is the ordered pair 0, 2. Lovely, lovely. Tell you what, let's graph this real quick. Let's say I bam, 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 bam. All right, there we go. Let's graph the first one. 3x plus 2y equals 4. There we go. All right. I had 3x minus 2y. 3x minus 2y equals -4. All right, and notice the intersection. Ooh, orange and black, Halloweeny. 0, 2 was my solution. There we go. And when I added those equations together, this was a new equation. All right. It's the equation of a vertical line, x equals 0. Actually, I just realized they might not let me graph this. X equals 0, they're not going to graph it. Oh, they did. It's the vertical line right here. Notice it has the same intersection as those two. So the fact that this ended up being a completely different equation didn't matter to me because the only thing I needed it for was to find the intersection, which I did. Success! Hooray! So there we go. Let's look at another example, shall we? Example. I've got this monitoring progress question 1 that we're gonna do together. All right, here we go. Yeah. All right, we're gonna do a few of these, and we're just specifically targeting steps 2 through 4 today. Here we go. All right, but let's verify that step 1 is done. Step 1, multiply one or both equations by some constant or just a number, right, is what that means. So that one of the variables, one of the like terms, one pair of them, has opposite coefficients. Which variable has opposite coefficients here, the x's or the y's? Which ones have opposite coefficients with each other? The x's do, right? Because positive 3x and negative 3x, the 3 and the negative 3 are opposites of one another. So step 1 is done. All right, step 1, you're done. You're done, step 1. You know that? You're done. Get out of here. We'll see you tomorrow. All right, so step 2, add them up. Here we go. Just add them up. I'm adding these two equations. That seems so unusual to us, but we are allowed to do it. All right. Yeah, 3x plus negative 3x is an ox. It's 0 x's. It's nothing. Perfect. They got eliminated. That's what we wanted. All right, add the y's together. 2y plus 4y is 6y, and then add the constants together on the other side of the equal sign. 7 plus 5 is 12. All right, I added them up. Step 3, solve that equation for whatever variable you happen to have left. So what do I do to both sides? Divide by 6, and I'll get y equals, oop, wrong color, Mr. Watte. Y equals 2. Half my answer. To get the other half, I don't have like a convenient revised equation that I could plug this in, so I'm going to plug this into either one of the originals. I'll just plug it in here because that'll avoid negatives. But you could plug it into this y, and that would have been fine. Doesn't matter. As my step 4. So let's see. So I'll have 3x plus 2 times y, which is 2, is equal to 7. So 3x plus 4 equals 7. We have so much practice solving equations now. It is crazy. All right, so what do I do to solve this? Do I deal with the 3 or the 4 first? Opposite of PEMDAS, SADMEP. Subtract the 4 from both sides. I like it. So I'm going to have 3x equals 3. And now divide by 3. Save that creation of possible fractions until the very end if you can. Right? No need to trudge through fractions, friends. And x equals 1. So my solution is 1, 2. Elimination method. All right, elimination method. And notice, if I was to solve this using substitution, which I'm almost tempted to right now, and just show you how much harder it would have been, because this would have created fractions. This would have had a fraction of like 2/3 in it. This would have had a fraction of like -4/3 or -4/3 or -3/4. Like, no, there was no weak spot. There was way too much body armor on this system, right, for solving by substitution to work effectively. It says to do a check, but yeah, to do a check, you would just plug this in for x and y and both of those and verify it works. For sake of time, because you guys have seen checks before, we're good. Let's do. I've got some problems for us from Prac 5.3b. So I've kind of swapped things around here. We're going to do a couple of these. All right. So this is where this is coming from. In case you're watching this and you're like, where is he getting this? This is not in the book. Here we go. Let's do some of these. So this is from Prac 5.3. I just wanted some more examples. All right. First of all, which of my variables in this first equation have opposite coefficients? The y's, right? Perfect. How about this one? Which ones have opposite coefficients? The y's again, all right? It's not always going to be the y's, but sometimes it will. Step 1 is done for each of these because they have those opposite coefficients for one of their variables, or as the book said, one of their pairs of like terms. All right, step 2, add them up. Here we go. Add them. 2x plus 5x is 7x. Those y's are eliminated. And 10 plus 11 is 21. Divide both sides by 7. Right, here we go. And I get x equals, oh, wrong color, man. X equals 3. That's a sad looking equal sign. That's a little better. All right, and that's half of my answer. To get the other half, you plug this into either equation's x. I'll plug it into the top one. Those look like friendlier numbers, but you could do either, right? Doesn't matter. So let's see, 2 times 3 plus y equals 10. 6 plus y equals 10. I'm just speeding through the algebra now since I want to just get to more of the process that we're doing, right? So even if after this problem, if you want to just watch and not write down the other ones. Oh, good call. Step 3 is solving this equation. You're right. So yeah, step 3 I did. Good catch, my friend. So y equals 4. Oh, aha. So the solution here is 3, 4. Right? Solved by elimination. Now this one, would you want to solve this one by substitution? It would have been a fine problem to solve by substitution, because notice there were 2 weak spots that I could have aimed for, right? So this one, you could have used substitution, you could have used elimination. Now, you do need to know all 3 types of solving systems, okay? So unfortunately, I can't just let you pick your favorite one and have you only learn one. I do need you to know all of them. That's what the rubrics will say, so yeah. Let's see, for problem 2. I actually, for my friends here in class, I'm going to say just watch, and I'll do this quickly and just kind of think about the process rather than trying to write everything down. And I've got 2 more examples I'm going to do after this, super rapido. So let's see, we had the opposite coefficients, add them up. 4x plus negative 3x is just an x. The y's canceled out, equals, that's negative 2. Oh, step 3, solve that for x. It is solved for x. X equals negative 2. We're done for the x. Plug in this, substitute it into either of the originals. I don't know, they're both kind of weird. I'll plug it into this one's x, I guess. So for step 4, substitute negative 3 times negative 2 plus 2y equals 14. So that's positive 6 plus 2y equals 14. Subtract the 6 from both sides. Fortunately, they've been giving us problems with nice answers. But both substitution and elimination method will work wonderfully, even if I have crazy fractions or radicals. It'll still work. It's just, you gotta have to, it'll give you accurate solutions every time. Y equals 4, right? So the solution here is negative 2 comma 4. Lovely, lovely. All right, let me do, yeah, both of these last ones are a little bit trickier. So we'll at least show you how to do those. So, all right. What's tricky about these problems is that if step 1 is technically actually not done. I just realized. Huh. Step 1 done over here? No, not quite. Not quite. So here, one of the problems is that my x's and y's aren't lined up. So what I'm going to do is rearrange this equation so that the x's are underneath each other, the y's are underneath each other, and the constants are going to be underneath each other as well. All right? So that's going to be like one weird additional piece, I guess I could call it, of step 1. The book's step didn't specify that. This I call this line them up, where you've got to line them all up into columns, and this one is not lined up conveniently into columns. Notice for these problems, I had my x's, my y's, my constant. My x's, my y's, my constant. The equal signs have to be lined up as well, by the way. And technically, the order, I could have had y equals constant and then x's. That's fine. It'll work. You just need them lined up so that when you add them up, they're gonna work out nicely. So what I would have to do is I need this x over there. So I'll subtract x from both sides. I don't know. I'm gonna, yeah, we'll do this one step at a time. That's fine. So I'll have 13 minus x minus 5y equals 0. And I want to move this 13 to the other side. I'll go slower on this one because, yeah, you guys should see how this one works out. And actually, maybe I'll even write what I'm doing. I'm lining up, line up like terms is what I'm doing for these steps, okay? And let's see, move that 13. Get it away! Get it out of here! And I have negative x minus 5y equals negative 13. So notice that benefits me in this way, that my x's are lined up. Now, I'm not going to require you to rewrite this equation down here, but it's probably a really good idea. Because when you start trying to add this to this and get something, and this to this and get something, and this to, like, you might make a mistake because there's so many things here, you might actually accidentally add the wrong things. So I'm going to recommend we rewrite this equation right here. X plus 2y equals 7. And notice that all of my like terms are lined up and my equal signs. All right, so now when I do step 2, first of all, do I have opposite coefficients? Did I actually get that? Right, the x's were opposite, +1 and -1. All right, so let's add them up. Add them up. Oh dear, that was crazy. Did you just see that? Oh dear. Ah! All right, let me go back up here and, all right, craziness. All right, so add them up. There we are. So x and -x is nothing, 0 x's. -5y and 2y is -3y's equals -13 and 7. Oh, man. 6? -6? I think I got it. Let's see. So notice this equation, what's nice about it is it has only one type of variable there. So let's divide both sides. All right, this is weird. All right, wow, I'm getting glitches here. I've got to end this video soon, I think. Yikes. Man. Oh dear. Wonder if it shouldn't have touch input on this. No, it doesn't. Huh. Weirdness. Okay, so if I want to solve for y, divide both sides by -3, I'll get y equals +2, and then I can substitute this I can really substitute this anywhere. I could plug it in this one, this one, this one. I already circled this version of that one up down there. I'm actually going to plug this into, I think the best place to plug it is right here. Why do you think I like this equation? Notice that this one is already solved for x. Yeah, so that's convenient. So let's plug it into that one and solve for that x. So I'll have 13 minus 5, and instead of y, I'll write 2, equals x. So let's see, 13 minus 10 equals x. Flip it around, I'll get x equals 3. And so my solution is 3, 2. All right. So sometimes you might have to line up your like terms. That was my only point. All right. So thanks for watching, Internet friends. Tienen un día el más bien del mundo.